Okay, I think we should be live now.
Okay.
Let me see it. Okay, let's go. So, hey everyone, today we have a talk from Prajwal on his recent paper at LLM Inference beyond single node. So recently, like scaling inference has become quite a topic, and as the models grow large, you have to scale between nodes, which becomes hard when you have parallelism strategies as TP. And this paper and this talk is about writing fast O-reduce and other communication primitives that work across nodes. They've also developed their own like small research like inference engine, which is really cool, and they've shown quite nice numbers being faster than NVLink on their setups. And with that, Prajwal, here.
Yeah, thank you, Mete. Today I'm going to be talking about low latency communication kernels for multi-node LLM inference with NVSHMEM. So a bit about me, I'm Prajwal. I'm a third year CS PhD student at UMD in the US. I'm working with Dr. Abhinav Bhatele in the Parallel Software and Systems group. My research interests mainly lie at the intersection of high performance computing and deep learning, primarily looking at optimizing systems for LLM inference. I've dabbled a bit in training. Recently, I've gotten interested into looking at these communication bottlenecks that exist, particularly for LLM inference, and that's what this talk is going to be about. So before we kind of get into the technical stuff, I'm going to briefly introduce the goal of this talk and a broad outline. This presentation is based on my recent work called LLM Inference Beyond a Single Node, from bottlenecks to mitigations with fast all-reduce communication. And the purpose of the paper and this talk is essentially going to be sharing our insights on the performance bottlenecks that we found when trying to scale multi-node LLM inference. And then to narrowing our focus down to the communication bottlenecks that exist in all-reduce communication, and hopefully showing how thoughtful NVSHMEM kernel design can mitigate these bottlenecks. The hope is that anybody who wants to write their own kernels in NVSHMEM is able to gain some insights from our experiences. The general outline of this talk is going to be, I'm going to talk about the background first and the results from our performance study when scaling multi-node LLM inference. Then the meat of this talk is going to talk about the kernel that we designed for all-reduce and what are the insights we got from that. And lastly, I'm going to go into the performance results and show how we beat nickel. Right, so let's get started. So just a bit of background. I'm sure a lot of people already know this, but LLM inference is this auto-regressive process where you where the model essentially traditionally generates one token at a time. And the input to the model at each generation step is the output from the previous step. Traditionally, it's divided into two phases. You have this pre-fill phase, where the model processes all the prompt tokens in parallel to generate the first output token. This phase, as you can imagine, is compute bound because you have a lot of tokens in your entire prompt being processed in parallel. So you have large matrix multiplications in the linear layers and the attention layers. After you generate the first token, what starts is the decode phase, wherein the generated token is fed back to the model again to generate the next output token. And this phase is more memory bound because now the input is just like a single token or a batch of few tokens. Your matma has become more skinny, and you spend more time loading in the weights of the model or the KV cache states, etc. Right. One of the problems in recent times has been that these models have been growing pretty large. And even though GPU VRAM capacity, HBM capacity has been increasing, you cannot infer state-of-the-art models on a single GPU. So you need to split the computation, the parameters of the model across multiple GPUs just to be able to run them. There are three primary strategies for doing this. This talk will focus on two of them. The first one is pipeline parallelism. So if you remember, basically your LLM is a repeated, like it's a sequence of repeating layers. So the easy, like one of the strategies is that you can have a set of layers on one GPU, the next set on the next GPU, and so on. And you'll have this input-output dependency, wherein you'll have to send the output of one set as the input to the next set of layers on the next GPU using point-to-point sends and receives. Usually what you do in this is you also break down your batch of tokens into smaller micro batches so that you can fill the pipeline and not have a lot of bubbles, and you can overlap the compute and communication a bit. Right. So the other strategy is tensor parallelism. So instead of like dividing it in sets of layers, what you can do is look into each layer, and you can divide the matrix multiplies within a layer across all the GPUs that you have. So what each GPU is doing is computing a partial matrix multiply in parallel. But now what you need to do is you need to aggregate the results. So you have these partial outputs. You need to sum them up across all the GPUs after each layer, after each matrix multiply. And that's done using an all-reduce communication, which incurs a very high communication volume. Lastly, for MOE models, you also have expert parallelism. Again, our work does not focus on MOE models, and we'll stick to dense models and the two previously mentioned parallelism schemes. But in MOE models, what you can also do is you have these experts, and you can partition your experts among the GPUs that you have, and then you need to have all-to-all communication to route your tokens to the correct expert. Right. So why do we need to study multi-node LLM inference? So, okay, so not everyone has a DGX box, a big DGX box with, let's say, 8 GB200 GPUs with the highest VRAM possible, right? So if you have that, you might be able to run like a big model on a single node. A node here is just like one machine or one compute unit with a set of GPUs and a set of CPUs. The GPUs are assumed like to be in one NVLink domain. But yeah, that's not the case for a lot of people. In fact, if you look at the traditional HPC clusters, they come in varying shapes and forms. So like here I've shown examples of like two of the HPC clusters that are popular. One is Perlmutter. So this is at the NERSC center. And I believe this has around 2,000 nodes. And each node has 4 GPUs, A100s, 40 or 80 GB, which are connected within a node by NVLink. But then across nodes, you have the slingshot network, which is 25 Gbps per NIC per direction. It's much slower than NVLink. And then the other system is like Vista. This is at the TAC supercomputing center. And you have like one GH200 per node here. So there is no NVLink domain, in fact. And then like the nodes are connected using InfiniBand. In both cases, it's a Dragonfly topology. So you can see that on these machines, you'll not be able to infer a model like Llama 3, 3.14 or 5B, or even larger MOE models. In fact, on Vista, I believe you probably won't be able to run like a 70B model also with a decent batch size. So you can see that you need to go beyond this NVLink domain and go into these slower interconnects. And it's really crucial to understand the performance bottlenecks that exist when you go into this domain. The standard way that people have scaled inference is, or the standard like knowledge is that you use TP within a node, so within an NVLink domain, which is fast, and then you use pipeline across nodes. This strategy is called hybrid parallelism. And like we're just looking at dense models here. Right. So I'll see if there are questions. If not, I'll just continue.
Yeah, so I kind of wonder like how this scales. Like, I suppose you were optimizing for the two systems that you were mentioning before, right? Like how it scales to, let's say, different, even supercomputing that have PCIe connected GPUs, right, inside a node, and so on. Like how it scales to those. Like, is
That
your framework like more general, I guess?
So yeah, one of the things is we haven't tested on sort of supercomputers where it's like even within a node that's PCIe, or it's not like it's very slow connects even within a node. In terms of, I guess it's generalizable to most of the supercomputers that we have worked with. So a lot of the DOE supercomputers have this architecture where you'll have 4 or 8 nodes or 4 or 8 GPUs per node that are usually connected in NVLink domain. And then I think in the US, most of them use a slingshot network by Cray. So it is generalizable to most of those machines. I would think that our sort of the kernel that I'm going to talk about is also generalizable to other interconnects apart from InfiniBand and Slingshot. But we'll have to like test it out, I guess.
Yeah, makes sense. Thank you.
Sorry, thanks. Yeah, so going forward, I'm going to present some results from our performance study. And I'm trying to keep this part short so that I can focus on the kernel design more. But you can find the extended results in the paper where we look at other models as well, like more scenarios, etc. So what we've tried to do here is we've tried to scale multi-node LLM inference on the Perlmutter system, which had like 4 A100s per node. We do strong scaling, which is where you keep a fixed workload and you increase the number of resources, GPUs in this case. So we're going all the way from 4 GPUs, which is a single node, to 32 GPUs, which is 8 nodes. For the Llama 7TB model, Llama 3.1 7TB model. And we have like 2 representative workloads, a prefill heavy workload and a decode heavy workloads. And we also have like a different number of prompts that we pack together in the workload. The workload is characterized by, like that we have this batch of prompts that we input to the 2 different LLM engines. And then we wait for the batch to be complete and before inputting the next batch. From a realistic scenario, this kind of workload is found in things like GRPO training, where you're generating rollouts, etc. So we compared different inference engines, state-of-the-art ones, so VLLM and SGLang mainly, and we use different parallelism schemes for that. There is also like you'll notice that there is like YALIS. YALIS stands for yet another LLM inference system. It's our own in-house prototype inference engine, which we developed for easier extensibility and instrumentation that can help us dive deep into the performance. Because what we found that like these larger code base are really difficult to work with in terms of instrumentation, etc. Yeah, so one of the expectations in strong scaling is that if you keep the workload fixed and you increase the number of resources, your time to solution should go down. But what you'll notice on the results on the right is that that does not happen. Any of the inference engines on any of these parallelism schemes, the time actually either like stays constant or it goes up in a lot of cases, and that's not ideal. So maybe it's just a hard problem, right? Maybe scaling inference is a hard problem. But if you look into it a bit more minutely, we'll see that there are like a couple of differences. So if you look at the prefill heavy workload, you will see that the parallelism schemes are a lot more closer, where you will see that VLLM's hybrid parallelism actually beats out at higher node counts the other competitors. But if you'll switch this and you'll go to the decode heavy workload and the more memory bound workload, you'll see a clear distinction between the hybrid parallelism and tensor parallelism. Um, so you'll see that like using hybrid parallelism, the time actually increases by a significant amount. But when using tensor parallelism just across nodes, you still don't get the idle scaling, but the time kind of is better than HP. So this was the first kind of surprising thing to us, and we wanted to investigate why that's happening. So we generated n-site traces, and we used this trace analysis tool from our lab called Pipit to dig in deeper. The plot here shows these performance breakdowns. So we look at the TP only case across nodes with YALIS here, and the hybrid parallelism case with VLLM here. And we break down the time into matmul, other computation, communication, and idle time. And there is like a bunch of analysis in the paper, but I'm going to go over the main things that we found interesting here. And we're looking at just like 2 and 4 nodes. So 8 GPUs is 2 nodes of Perlmutter, 16 is 4 nodes. For the 2 different workloads that we looked at earlier. So the prefill heavy on the left and the decode heavy on the right. So the first thing that you'll notice is in the prefill heavy case where you have a lot of compute, both for TP and for HP, when you increase the number of GPUs, the matmul time actually goes down. This is an expectation. This matches the expectation that you put in more resources, you've divided the compute in both tensor parallelism and in pipeline parallelism through microbatching. So the time for matmuls will go down. But interestingly, if you look at the decode heavy case, the time for the matmuls goes down for the TP case, but it remains almost constant for the hybrid parallelism case. And this was like very surprising to us. So we wanted to dig in a bit more deeper, and we isolated one of the matrix multiplies in the decode phase, in the decode heavy workload in the decode phase. So just like stepping back a bit, a gem can be characterized by the dimensions of its input. So if you're trying to multiply 2 matrices A and B to get the output C, you can, where the input A is M cross K and B is K cross N, the matrix multiply can be characterized by like M, K, and N. In this case, like N was the same for both of all these cases, so we don't show it here. But what you will see is that in decodes, we expect the M to be small because you have like less number of tokens, right? So it's a skinny matrix that you're trying to multiply with your parameters. And the blue bar here shows what will happen in the pipeline parallelism or hybrid parallelism scenario, where you will microbatch. So you'll divide your M further down into smaller microbatches. So you'll reduce M from 32 to 16 here. Whereas the green bar shows what will happen in TP, where you'll actually divide your parameters and you divide the inner dimension by half. So it goes from 57344 to like 28672 here. And what you'll see is the blue bar shows no decrease in time at all for the gem. Whereas for the green bar, you see the expected decrease by about like a half or less than half. And this is interesting. This is possibly because your matrix multipliers are tiled, and the skinnier you kind of go in one dimension, you do not gain anything by reducing that dimension further. So this is one of the reasons why in the decode heavy scenario, pipeline might not be a good option. Lastly, if you look at the communication times, right, and this is where we'll take the talk further, but you can clearly see that all reduced communication in TP case is like really bad. And bear in mind that we're comparing it with hybrid parallelism. So there is still all reduced communication happening within a node, which is because you use TP within a node. But that is still small. But the jump in communication as soon as your all reduce goes beyond a node is like massive here. And this is what we'll kind of focus on in the rest of the talk and motivates our main work. Right. So focusing down on this like communication bottleneck in TP. So yeah, we wanted to focus on this decode heavy scenario where TP can actually win for the workloads that we studied. When we looked at the method sizes, you can see that for prefill, the method sizes are in the hundreds of MBs range usually. But for the decode, you have these like smaller method sizes in the tens to hundreds of KBs. For example, in the previous case, the decode heavy workload, the method size was 128 KB. If you'll increase the number of if you increase the number of prompts in your batch, it'll go up to like let's say 1 MB or something like that. So we wanted to see if nickel is the problem and what's happening with that all reduce when you go beyond a node. So we benchmark nickel against Cray MPitch on the Perlmutter system for like a range of method sizes. We show like two representative ones here. And what you will see is, yeah, for some method size like 128 KB, nickel might be better than Cray MPitch, but then as you start increasing it to let's say 512 KB, it starts performing worse than even MPitch. And bear in mind that like MPitch is probably not using the most optimal kernels. I believe it's like doing the reduction on the CPU. Whereas nickel should really be optimized to do stuff on the GPU. So this is not ideal at all. Yeah, so it scales poorly and it's slower than MPI in some cases and in the method sizes that we care about. We kind of hypothesized why this could be the case. So one of the things is that nickel has only two algorithms, two main algorithms for all reduce, ring and tree. There are other variants that require specialized hardware. There's NVLS, there's CallNet and all of that stuff. But I think that requires like, specialized hardware. So we'll focus on like these two algorithms, which are more general and like are used in most cases. Whereas MPitch has more algorithms, and it kind of uses this like recursive doubling approach in this range. So we thought maybe that's the reason why nickel is not performing as well, because it's using a suboptimal algorithm. Now, a solution could easily be that you use MPI instead of nickel for this part of inference. The problem with that is like standard MPI implementations don't have support for things like CUDA graphs, which are really critical for inference performance. So what we asked ourselves is, can we write something? Can we write a communication kernel ourselves that has like CUDA graph support for inference and is also like using an optimal algorithm? So after a couple of tries, actually, we came up with this approach. It's called NVRAR, so NVSHMEM-based recursive all reduce. And we came up with this three-phase design. In the first phase, you have a intranode reduce scatter within a single node. So it's on an NVLink domain. In the next phase, which is where we actually write a device kernel using NVSHMEM, where we do a recursive doubling all reduce between corresponding GPUs across the nodes. And then lastly, to get the results correctly, we do an intranode all gather. I'll go over like this in more detail in just a couple of minutes. But I guess I'll pause here and see if there are questions about the previous part, and then I can move towards the next thing.
Yeah, I have a question. Like as you were saying that, like with decreasing the, I believe it was m dimension in the matrix multiply, you don't get any speed up, right? But when you decrease k, you get like a reasonable like 50% speed up, or whatever that was. Have you actually tried like exploring, like writing your own matmul for this case, or like trying to find a better matmul? Because I believe like it shouldn't. I think the like decreasing the m size should be worse than decreasing the k size, as you saw, but shouldn't be that bad, right?
Yeah, that's true. So that's something that we haven't explored much. In fact, that's planned as follow-up work as to see. I think in general, one of the things is like skinnier matmulls and like tall and skinny matmulls are harder problems than like more uniform matmulls. What we basically hypothesized is that it's something to do with tile sizes. Like if your tile size is, if you're decreasing your M below kind of like a minimal tile size, then you don't really get any advantage of doing that. Um, Whereas like K is like really huge, so you can like have much more of an advantage there.
Yeah.
But yeah, it's something like, yeah, looking at maybe papers as to if people have solved this problem of skinny matmulls and trying to plug that in into pipeline parallelism might be a strategy of improving that. And we definitely kind of want to look into that.
Yeah.
But
Makes sense. I also wanted to ask about if you can go back like 2 slides, I think it was. No, just one slide.
okay.
And so there's is this already like you were mentioning that you wrote your own inference engine like the Yalis? Is this already using Yalis, or this is just standard VL and plugin?
Oh,
I'm
so
not sure
this
how to
is,
work.
oh,
Or this
so,
is just
okay.
like this is just per like this is just all reduced, right?
Yeah, this is
Yeah.
just all reduced. So this has
Yeah.
been, this is like outside an inference engine. So we use the nickel tests benchmark suite. And there's OSU benchmark
Yeah.
like suite, which is like pretty popular for MPI. So we use both of them to generate these numbers. So these are like isolated from any inference engine or something. So this
I
is
see.
purely just looking at all reduced performance.
I see. Thank you.
Uh, yeah. So yeah. So just a bit of primer on like what NVSHMEM is. So NVSHMEM is this parallel programming interface based on OpenSHMEM from NVIDIA. It's based on the PGAS model, and I would not go into like a lot of detail into like what that model is, but essentially, um, you have this you like logically shared global address space, like one global address space, which is partitioned across your different GPUs or processing elements, as is the as like the terminology with NVSHMEM. So yeah, like it's basically each P can access the remote P memory as if it was its own memory using like some APIs, of course. So it can do a put uh, or a get on the remote memory API as long as it has the pointer to that remote memory API and stuff. And NVSHMEM basically provides you like these host level and device side APIs to do these like remote memory access operations to move the data between Ps. Um, and I'll go over like more of NVSHMEM APIs as I go through the design of like NVRAR. But before I kind of like start looking into the design details, the insight that we had with NVRAR, I just wanted to like show this API of NVRAR and to show you like what we do. Um, I hope it's visible to everybody. It's not too small. But yeah, this is an initial API. It's subject to change and stuff. But oh, sorry. Yeah, but what you essentially need to do is you need to first have some sort of like distributed environment that's initialized either using Torch or MPI. We don't handle that. We expect that you already create like multiple processes. You have a process management system. But given that you have that, you will get these unique IDs. So we use NVSHMEM has different sort of initializations. It can initialize directly using MPI. I believe there are like other initialization techniques, but we use this unique ID based initialization, which is pretty standard. It can work with like Torch distributed. It can work with MPI and everything. So yeah, you get this unique ID from the NVSHMEM like NVRAR wrapper. Then you create a communicator like you will create a nickel communicator using this unique ID. What you'll have to do before that is share this unique ID among like all the processes that you want to be in that communicator. So that's like either you can do it using MPI or you can do it using Torch. So this is like the initialization part that's required to create the communicator. Once you've done that, you can basically ask NVRAR on this library that we have for a tensor. So you give it the tensor size, the D type, the device that you want the tensor to be on, and it'll give you like this tensor, which is like a torch tensor in this case, and this ID. The reason why we do it this way is because you need to allocate these tensor using NVSHMEM-malloc, which is necessary to be able to like communicate over them using NVSHMEM. Then our kernel has a bunch of like parameters or hyperparameters that need to be tuned for performance. So this includes like the blocks that you'll launch. There's a protocol that I'm going to talk about later, like the thread block size, and there's a chunk size. So you can set that. We also like provide tuning scripts that you need to run for each message size, like node count configuration once to get the optimal parameters for performance. So you can set that, and then once you've done that, you just need to call like an all reduce. You give it the stream, you give it the tensor ID and stuff. And then once you're done, you can like free the tensor and you can destroy the communicator. So this is like a high level overview of like how the code looks in terms of using it. Now I'll go over like the design a bit. And what I've tried to do here is I've tried to mark things that I feel are general enough for other people writing their own kernels in NVSHMEM, and like they're useful for them like as insights. So on the left, I have the code for NVRAR, like pseudocode. And this is the driver part of NVRAR. So this is the high level function which calls the three phases. So I'm going to go over that first. So what I'm trying to do here is I have a message M, which I'm trying to reduce over all the ranks. I have G GPUs per node, and I have like N number of nodes. There are a couple of hyperparameters, as I mentioned, like chunk size, and then the other stuff I'll go over as I go over the design. But yeah, so looking at the three-phase design. So the first thing that we do is do a reduce scatter. So for people who aren't aware, reduce scatter is this operation where you have like data on all the GPUs. You do a reduce, but you only keep a portion of that data after the reduction. So this is like shown here. Now, this was important because what we wanted to do is reduce the message volume that will go into the internode phase. So whenever you're designing like internode kernels, you want to minimize, especially for latency, you want to minimize the internode message volume as much as possible. So doing this reduce scatter makes that every rank within a node has different data elements, and it's reduced by like G here. And then if we communicate over this, your communication has reduced by G across nodes. So this is like a better choice than doing a two-phase design where you would have done an internode all reduce, let's say, where everybody would come out with all the data. And then do a internode all reduce. For this, we use this NVSHMEM host API, NVSHMEM-X, whatever type name, like BF16 here, some reduce scatter on stream, and internally it actually dissolves to a nickel reduce scatter because it's in an annealing domain. Yeah, then comes the internode phase, and this is where this, like we call our custom kernel, which we call RD inter here. So recursive doubling is this like logarithmic approach where at each step, pairs of GPUs exchange their data and do a reduction. And then on the next step, you will go to the next 2 to the power ith pair that you have, and you'll exchange data with it. Finally, after the logarithmic number of steps, every rank should have like the reduced data. Yeah. So as I said, it's like, so this is where we have the custom NVSHMEM kernel, and I'm going to go over that later. So this is the algorithm that MPitch uses for like short and medium sized messages, whereas Nickel uses some other algorithms. Primarily, Nickel also uses this logarithmic latency algorithm called like tree all reduce, where you do a similar kind of reduction, but it's a two-phase reduction. So you do a reduction, you still kind of distribute your nodes into a tree, and you do a reduction up to the root, and then you do a broadcast, uh, giving the reduced result to all the ranks. As opposed to that, what we have is like the recursive doubling approach is like a one-phase approach. So you expect like messages to be just exchanged once instead of twice. And the hope is that this will be faster. Finally, so now after those two phases, each rank or a node will have part of the globally reduced data. They won't have all the data. So you just need to do an all gather to get the final data on each of those ranks. And this again is done through an NVSHMEM host API called NVSHMEM fcollect. And this again kind of boils down or dissolves to a Nickel all gather call. So one of the questions that people might have is that why did we not go with a fused approach, wherein we just write one kernel that does all of these three phases, and we don't pay this like kernel launch latency again and again. And that's definitely possible. But while developing the kernel, what we found that when you're working with heterogeneous networks, so like NVLink and some other interconnect across nodes, the kernel launch parameters, the block size that you need to launch, the number of thread blocks that you need to launch, kind of need to be different to optimize communication in that like domain. So while it is possible to write a very complex kernel that takes care of all of that, we found it a lot easier to have separate kernels wherein each of those kernels can be optimized for the domain that they're operating in. And of course, Nickel is really optimized within a node. So this gives us like the benefit of just using Nickel where it's optimized and then doing something where it's not optimized. If people want to write a fused kernel, yeah, that like, and they have ideas on how to do it, like please let us know and we can look into that.
Yeah, sorry to jump into that. Like this, so I wonder, like you said that you didn't want to fuse the kernels to like because the communication profiles intranode and internode are way different. But so as I understand, couldn't you fuse the recursive doubling with the all gather itself and just have the first reduced gather be NVLink or like the default Nickel kernel?
Yeah, as I said, like there are like I think there are like still scope for more optimization here. So I would not say that this is like the most optimized version that we've written. What we found that this was like a lot easier, especially also because you have to care about synchronization, right? Like, so when you fuse it within the kernel that we've written, let's say you were to fuse the recursive doubling and the all gather, you need to make sure that the all gather does not happen before all the sort of ranks have the data that needs to be there, or like the data that needs to be sent out has been sent and like has been received and reduced. So like for that, either we had to add like fences using NVSHMEM or like quiet operations within a kernel, and what we noted was like, or like have basically synchronization. Like if you're launching like multiple thread blocks, you need to make sure that all the thread blocks are done in a certain way, like for like a certain chunk of data, let's say. And we found that like having that synchronization leads to bad performance. There is still scope. I think there is like a way to do it, but it's just like in terms of ease of programming, we found that this is like a lot easier, and we were still able to get a decent performance out of it, like pretty good performance actually. So this kind of balances like performance and ease of like writing and maintaining the code. Uh, but yeah, I definitely think that there is like more to do here. Especially, I mean, I think in like a lot of these inference engines, people have found that even nickel, like using nickel, like call reduce or like within a node is not as optimal. And you can do other approaches, like you can just do like RDMA operations. You can do a one-shot all reduce or a one-shot all gather. That's written using like CUDA IPC, for example. So that is definitely something we want to look into, is to replacing these all gather nickel calls with like one-shot calls and see how much of a performance gain that gives us.
Yeah, that was like my second question. Like, if
Okay.
you've if you've like played around with basically tuning the reduce scatter or like the all gather that just dissolves the
No,
nickel.
so yeah, that, as I said, like that's on the agenda. Like we
Yeah.
really wanted to first nail down on like reducing the main bottleneck, which is the internode communication. And the good thing is that our design is modular enough, so you can replace that reduce scatter call with like whatever custom kernel you want to write, and then you can replace it with a one-shot all reduce scatter and a one-shot all gather, and try to then fuse them in.
Yeah. Thanks.
Thank you. Yeah, so this is kind of like the three-phase design that we had, but of course, this is not enough to get good performance. And on top of these, we made like several optimizations, several other design and implementation choices that we found were important to get good performance. So yeah, like the first optimization, again, looking just at the driver code for now, is that you need to synchronize. So you'll notice that we have these B send and B receive buffers. So of course, we want to pre-allocate some buffers for each tensor to store the intermediate results, the results after the reduced scatter, the results after the all gather and stuff like that. But when you have successive all reduced calls, you want to be able to safely reuse them. And to do that, you need to have like some sort of global synchronization. You don't want to create new buffers every time, of course, for each call. And one option to do this, actually stepping back a bit, NVSHMEM gives you these put and get calls, which can be non-blocking, and that's what we use here. So you need to make sure those operations are complete and the buffers are safe to reuse. One option, or the standard option, is to use NVSHMEM quiet. This ensures completion and visibility across all the ranks that are participating in that, that are communicating messages. So it ensures anything that's been transferred or transmitted before the quiet operation will be completed and visible to all ranks. But what we found is that this is a very costly operation. Like it would totally tank our performance. So we would like recommend anybody using this to use this as least as possible. The other thing is, if you go into the minute details, it forces a synchronization among all the ranks. So it's like, so if you have a communicator among all your GPUs, it forces you to synchronize with all of them and not just the peers that you need to communicate with. So in the logarithmic number of steps, you only need to communicate, let's say, with 2 peers, but you will synchronize with all of them directly. And so this is a very coarse-grained synchronization between all ranks. What we did was a bit different. We assign each all reduce operation a unique sequence number. And we have this observation that all you care about is that the peers that you communicate with have, done their job. So you can go ahead with your job. So you only need to do a fine-grained synchronization between your peers. So instead of calling an NVSHMEM quiet, what we do is we synchronize over the sequence number. So before the start of every, and we do it at the start of every all reduce operation, we see that the other peer ranks are done with the previous sequence number or not, and we wait till they are. This is implemented using atomics in NVSHMEM. So these are the two like APIs, NVSHMEM UN64 atomic set, which allows you to atomically set a value on a remote P, and then like uh, the local P does a wait till it sees the correct value. Um, One crucial thing to note here, and this is something that I think will come up more and more now, is that we found that the NVSHMEM quiet is especially slow on slingshot networks, which is using the lib fabric transport in NVSHMEM. And this is because the lib fabric transport in NVSHMEM is not really um, implemented very efficiently, or it does not use all the hardware features that, let's say, slingshot provides. So slingshot, for example, has the ability to do uh, like ordered delivery of messages. It has hardware fences. But right now, like NVSHMEM does not use that, which makes it like even more costly there. Right. So before now I go into the main kernel, I'll give a primer on like the RMA operations that we use. So NVSHMEM's device side API allows this in kernel one side put and get operation. That's how you like transfer data between Ps, as I mentioned. Based on their guide, using puts is better than gets. So that's what we do. They have a blocking API and a non-blocking API. The non-blocking API is marked by NBI, and we found that using the blocking API is very slow. Blocking essentially, I mean, if you block, you will not like it'll block till you can reuse the buffer, but otherwise it'll return immediately, and then you have to make sure that the buffer is not like buffer is like maintained while you do other stuff. But yeah, so there is two APIs broadly. There is a NVSHMEM put signal non-blocking API, which does a put, and then it also atomically writes a signal to the remote P. And this signal is what you can use to detect on the remote P that, hey, I have received the data and I can go ahead with my reduction. The other is just a standard put. So there's no signaling involved. Like you can just put the data, but then you'll have to have some way of synchronizing or like the remote P knowing that this data is the correct data that I'm intended to receive, and I can start with my reduction. Also, there are like these two, like there are multiple variants of these APIs. So there's a warp variant. So tradition, like the normal one will be operated by a single thread. But then you have these warp collective API, which will be operated on by a block, like a warp of threads. And then like the block API will be operated cooperatively by a thread block. And we found that like for proxy-based transports, using the block API gives us the best performance in the intranode scenarios. So you should try to use this as much as possible. Even I believe on intranode, this is recommended to use the block APIs. Right. So this leads us to the second optimization, right? So one of the things, like when using these puts, right? So one option is that you can just put, like you would assume that since you have these small method sizes, you can just take all the method sizes and put everything in one message and just send it. But we found that that's not the case. So we introduced these hyperparameters. Of course, you have like the number of thread blocks and like this chunk size parameter. So parallel thread blocks work on independent data blocks. And what this allows is like one thread block can be issuing the put request while the other has received data and it's doing the reduction. So it allows for like coast grain, like overlap between reduction and communication. But even within a thread block, what we do is we chunk the data, and this chunk is sent in one non-blocking put. And we notice that this is essential because it helps us control, I guess, the network injection like size, like how much data am I putting in one put call. And what we found that these parameters have a huge impact on performance. So you can see here that, having like different block size. So I'm trying to do an all reduce on 1 MB message on 16 GPUs. And you can see that like chunk size, having like a big chunk just sending all the data at once is like good here, but then it's like here it's not the same, right? Like having a bigger chunk size helps, but it's like still not as big as the original like message size. So having like this variability or like this ability to tune the chunk size is important, and so is the number of blocks. Um, the other thing is that you want to allow for asynchronous progress between peers. So let's say one peer was done talking, like was in step 0. It received data, it sent data to its peer, it has received all the data, it has done its reduction. So it now wants to start sending the data to the next peer in the next recursive step. So it does so what we did was, in order to not have this rank wait, um, we have multiple sends and receive buffers. Specifically, we have as many sends and receive buffers as there are the number of recursive steps, which in this case is going to be log n. The good thing is, like, since we're operating on like small message sizes here, like up to a MB, this overhead is not large. So it's really not that big of a problem here. But yeah, for large messages, this can become a big memory overhead. Right. So the last thing is looking at synchronization between steps. So earlier we talked about the global synchronization between two all-reduce successive calls. But even within a single all-reduce operation, you might have guessed that the recursive steps require some synchronization among the peers, right? You need to make sure that the data that you have from the other peer is ready before you reduce it into your own local data. And as I mentioned earlier, either you can use the put signal API, which was an option. But what we found is that is again very slow. So signaling in NVSHMEM is pretty slow. And specifically, as I mentioned previously as well, for the slingshot network, it can like incur up to like 1.5 times the round trip time, just because it's not using hardware fences, just because it's not using a lot of the features that the network has to offer. And this is like a great actually like commit. So NVSHMEM became like open source recently, and a lot of people have like contributed to it, like trying to improve it. And you can read a bunch of like these commits and like the messages that they have. So this message that I've linked here will like kind of show you like this observation. So yeah, like it was kind of lucky for us that we found this. And that's why we deviated our focus to like not using the signal API at all. What we do instead is we use Nickel's approach. So Nickel has this LL style protocol or low latency protocol, where you don't do explicit synchronization or signaling, but what you do is you pack in the data that needs to be reduced and flags that tell you whether the data is valid or not in the same payload. In this case, it's an 8-byte payload where the first 4 bytes are the data. So if it's like a FP16 data type, it's going to be like 2 FP16 numbers, and there's a 4-byte flag. Why does this work? So, and this was like very interesting to me, but 8 bytes is essential here because most networks and most 64-bit architectures, including GPUs, CPUs, operate in 64-bit land. And that's why 8-byte operations are usually atomic. So you can be pretty sure that your 8-byte data will not be split into smaller packets. If it was split into smaller packets, what you can end up with is having the flags received earlier than the data, because NVSHMEM has no guarantees on the data ordering in general. But because these operations are inherently atomic, that problem goes away. And this is in fact this is in fact a property that even Nickel depends on. So Nickel's LL style protocol also relies on this. So yeah, you need this 8-byte payload, and this helps you do the synchronization without calling the Signal API, you can just call puts, and you don't need to worry about like data flag memory ordering across devices. So what we'll do is we'll wait on this flag. We'll see if it's equal to the sequence number in the current step. If it is, then the data is valid, and then we can reduce it to our local data. Right. So these were the three main optimizations that helped us achieve good performance. And now I'll kind of show you the results and the performance that we achieve. So right, this is, so we first benchmark our kernel independently outside an inference engine against Nickel. So right, so this time the benchmark is written in PyTorch because we wanted to use CUDA graphs here. And we're benchmarking against Nickel 2.27, which is, I think at the time was the latest one. We do it for two machines that I mentioned previously. So Perlmutter, which has a slingshot network, 4 NICs per node, and Vista, which is InfiniBand, 1 NIC per node and 200 Gbps in that case. So what you'll notice in the results is basically the blue line is Nickel and the orange line is NVRAR, and we are quite faster than Nickel in these method sizes that we care about. The paper has more detailed results. It has like more method sizes, and I think on an average, we see around like 1.5 to 2x speedups on Perlmutter, and then 2 to 3x speedups at times on Vista. We also kind of wanted to understand like these trend lines. So we modeled the communication, and this is like one of the, like there's this alpha beta model to model communication, latencies and bandwidths, and the time it takes for a collective. So I've like shown that here. This is just looking at the latency terms. And effectively, NVRAR has this log latency terms in terms of the number of nodes multiplied by the internode latency. Nickel's tree algorithm has a logarithmic latency term multiplied by the internode latency, but there's also a factor of 2 here. And ring is like not great for these mesh sizes because you have like a linear latency term in the number of nodes. But what is important here is these two terms are like similar, but there's a factor of 2. And this actually replicates itself in these graphs, because if you'll see, the x-axis is doubling, so it's logarithmic, and you expect the time to be a linear line here. And you essentially see that both of them are actually just like approximately straight lines. But NVRAR is like has a smaller slope. It aligns with this like theoretical result as well. Then we integrate this into Yalis now, and we run our experiments like our scaling study again. We again measure the time to completion of a given batch of tokens, a given batch of prompts, and we like report the relative speedups that we get while using NVRAR against Nickel. So you can see for the 7TB model on 32 GPUs, which is 8 nodes, we can get up to like 1.8x times the speed up. And for the 405B model, again, like on 64 GPUs, which is like 16 nodes, you can get up to like 1.72 times the speed up in end-to-end time. And finally, we also wanted to, of course, look at like where is the speed up coming from? So we again created these performance breakdowns, and we saw that for as you like increase the number of prompts, you get like up to a 50% reduction in communication, and that's where most of the speed up is coming from. And it's indeed coming from the communication time. Yeah, I think. Yeah. So any questions up till now?
Yeah. I like regarding this last graph, like as you were showing before, like the difference between your algorithm and basically nickel is just in like a factor of 2, right? So with that, I'd assume that like as you scale the message size, you go further and further away from like the latency bound regime.
Yep.
So the scaling factor, like the factor of 2, is going to matter less and less, right?
Yeah.
So I would assume that your algorithm is going to perform very well on a small message sizes, and then it's going to like degrade basically per time, which kind of makes sense. Like, and I suppose it's expected. But I wonder, like on the last slide, you were showing that the communication didn't really.
This one?
No, the last one, which was this one, yeah.
Okay.
So when you have like a really small message size, your algorithm basically isn't that much faster than nickel.
Makes sense, yeah.
Do you have a hunch for why it is? Yeah, sorry.
Yeah, that's actually a great question. So there is actually a sweet spot. So I don't have those results here. Maybe let me see if I have them. No. Oh, sorry. I don't know what happened.
Okay, worries.
Just okay. Oh, yeah, it's there. Yeah, so actually, if you look at the paper and we have those results, so technically there is a range initially. So let's say if you look at this very small message regime, which is 4 bytes to like around a 128 KB, where our algorithm is not as fast. It's actually like maybe slower than nickel in some sense, in certain scenarios in our independent micro benchmark. And the reason for that is, of course, like as I said, we have multiple kernels. So the the theoretical results kind of do not take into account things like number of kernels that you have. So the alpha values right now here that I've assumed are kind of the same, but they're actually not the same. These alpha values will depend on not just the network latency, but the latency of your like implementation in a certain sense. If you have more kernels, this will be higher. There's also a constant factor that you have to include here. So what we believe is happening is that the smaller, very small regime, let's say like 64 KB and stuff like that, your constant factor that the overhead that you have is playing more of a role in the latency than even this factor. So the sweet spot is more in the 256 KB to 2 MB range, where you'll see like larger speedups. Yeah, and that's why you see this difference, like where with 8 proms you don't see as much gain.
Yeah, makes sense.
Yeah. Actually, on that point, we do want to improve it. So, as you suggested earlier, like looking into improving the intra-node collectives like reduce, scatter, and all gather, replacing them with like an one-shot approach, or maybe trying to fuse it again, is something we want to look at to further kind of narrow the gap or like increase the gap that we have in performance.
Yeah, I suppose fusing it would help in these like really small message sizes, I guess.
Yep.
Yeah, I mean, I guess that was like also one of my questions, like which what are like the next steps that you see in this?
Yeah, so that's a good question. Again, as I said, there are a bunch of things that we plan. One thing very clearly, so one of the issues with the LL style protocol that we are running is, of course, it increases it adds redundancy, right? So now you're like using like half of the total message size to actually send important data. And we went with what Nickel does right now, which is a 4 byte flag and 4 byte data. But we realized that's not really needed. You can like have your flag to be very small. You can have like just a 2 byte flag, and that increases your message like efficiency by a significant amount. So improving that. changing the intranode algorithms to one shot. I think those will help us further have better performance than nickel here.
Yeah, thank you. I guess if no one in the chat has any questions, I guess that's going to be it. Thank you very much for the talk. If you want to go through these takeaways, sorry to cut you off.
So I tried to basically just try to some of the takeaways that maybe are useful for other people when we were designing our kernel. So there's a big list, but effectively try to reduce your internode message size as much as possible. Try looking for the optimal algorithms for the message regime that you're operating in. That's used by different communication libraries, not just Nickel, RICL, etc. For heterogeneous networks, maybe having multiple kernel instead of using a fused approach might still give you good performance. Puts over gets, that's what NVSHMEM recommends, and then use non-blocking versions as much as possible. Avoid NVSHMEM quiet and fence operations wherever you can. They're very expensive. Avoid explicit signaling. Try to look for alternative synchronization strategies, reducing synchronization as much as you can between the ranks. Then chunking data, tuning kernel parameters are very essential for performance. And then some transport backends, as I said, like libfabric, are very under-optimized right now. So if you can contribute to NVSHMEM, improve them, that'll be great. I think those are the main takeaways that I found. I think would be helpful. That's kind of it. And you can find our work here, the code for both of for an inference engine, for our AllReduce, and the paper, and more stuff that our group does.
Yeah, thank you very much. I'll be uploading the slides to the GPU mode repo as usual. So if you want to find them, it's going to be there. And thank you everyone for joining.
Thank you so much.
And have a good one.
Have a good one. Thank you so much for this opportunity.